Okay, welcome back to machine learning. We just finished the second midterm, and I guess we only have 5 classes left, which is kind of crazy. I can't believe we're almost at the end of the term now. And so I was taking a look at what is left to cover, and honestly, like the things that was covered the years before and what was planned was just this, okay, so there's 5 lectures left. That's what I have on the screen here. And this is kind of all that was really left to be covered, honestly, from the last years and stuff. And then I looked through this, and I don't think there's any way I'm going to spend 5 classes covering that, or 4 classes. So I think we'll actually be done this today, like this binary classification stuff. So we've already like set ourselves up with everything from before, and you'll see that it's like everything kind of is the same. You just change the loss function. So that's going to be great. So we'll finish this. And then we can do what is called multi-class classification, which is just like a natural extension where you have more than 2 classes. And this, I guess, wasn't covered before, but it's a very natural like extension. And this gets into some more exciting stuff because once we cover that, we're almost in a place to understand how all this language model stuff works, like ChatGPT and stuff. So I think we will actually get to that. And then I think we'll also have time to cover these neural networks. So we'll also cover neural networks, which should honestly be fine to do in one lecture, like the high level and then just like the main details that you need to know about this and not get into too many like, I don't know, nuances. But yeah, so I think this is very possible. And we're doing pretty well with time stuff. So yeah, that's the plan. And this should all be on the final exam. But like these things, it's not going to be like super advanced, but like I think you should at least have an understanding of what's happening now, hopefully by the end of this course. Okay, so that's the hope. We'll see what happens. But today we do binary classification, and hopefully you finish that. And assignment 7, okay, so assignment 7 is going to be another coding assignment. And that coding assignment is going to be based on like binary and multi-class classification. So you're going to get to see these things called like decision boundaries where you pick one class or the other and stuff like that. And yeah, so it'll be based on these 2 things. And notice that this lecture is on Tuesday, but the assignment's due next Friday. So unfortunately, you kind of will only see this content a few days before it's due, I guess. Anyways, so that's the story. And the other thing to note is that there's no tutorial today. There's not much to really cover quite now, but next week we'll go over like the midterm and some like questions about the midterm and maybe some other things. Okay, so that is the story. So let's get into this classification business. So yeah, let's begin. So far, we've spent a lot of time, it's like 20 lectures, talking about regression almost always and predicting these house prices. But there was a little bit of a discussion in the very first class and when we talked about supervised learning that the labels don't have to be these real numbers. They don't have to be like just numbers from like negative to positive infinity or whatever. They can be what is called like classes, and this is called classification setting. And in particular, like it's more formally when the labels are unordered. And usually it's like this finite set of unordered objects. And the example, which you're going to see in the assignment, and we've talked about a little bit before, is like, for instance, you want to predict the type of wine you have, let's say, based on some information, like some features, which say is the chemicals in that wine. So you get some information like you have this much of this chemical, another chemical, and so on. And you need to just predict these 3 classes, which is either it's a Barolo, a Grignolino, and a Barbera wine. So there's like 3 classes, let's say. And there's no notion of ordering. It's not like if you predict this, you're actually closer to this class than this class or something like this. So this is very important, the difference between regression and classification. Okay, the other difference is we no longer had this like need for this squared loss and stuff. We just, like the natural loss function, L, was now the 0, 1 loss, which just says, did you predict the class correctly or not? Because if you predict it incorrectly, there's no notion of being close anymore. It's just you're wrong. Okay, and that's described in this way, which is you have a loss function, it has a prediction y hat as its input and the true label y, right? And so you have 0 loss, so you predict it correctly. This means y hat equals y. So then you have, in that case, you have 0 loss. That should make sense. And in every other case, since there's no notion of being closer to a label than not being close, you just have a loss of 1. So this is like the loss we're interested in this classification setting. Okay, and we're going to quickly see that this loss doesn't work so well for us, but let's just look at it. So what does this loss kind of look like if we fix a value of y? So let's say the true label is y equals 1, right? So in this case, this would be like this Grignolino y. Well, then it depends on what your y hat is, right? So like the x-axis is y hat. And so if you predict 1 with y hat, like if y hat is 1, well, then you have 0 loss. So that's what this black point shows here. However, if y hat is anything but 1, in this case, there's only 2 other classes, which is the class 0 and class 2, then you end up with a loss of 1, which is what's shown here. Okay. The important thing that I want to highlight, and I don't go into too much detail, is that this function, especially when you fix y, is not a continuous function. Okay. So this is what I want to show. And you'll see why this is important in a very quick second. But okay, so we have this like loss, whatever. Let's try to do the things we were trying before, which is we want to minimize the estimated loss, right? Like this thing is an estimate of the true expected loss. So what is the estimated loss? Again, this thing is just the sample mean estimate of the loss function. So we could try to minimize this, but then what you'll see is like, at least with the techniques we've seen in this class so far, is that first of all, this loss is again, since it's using the 0, 1 loss, this thing is also not continuous, especially, well, yeah, it's not going to be continuous. You can pick whatever you want for your predictor. This loss is just going to jump between 0 and 1. It's going to have like this disjoint jump between things. And what that really means is that all the optimization techniques we've seen so far have always assumed that things were continuous and that we could take derivatives and then we could set them to 0 and so on, or like do gradient descent and stuff. And you can't really do this with the 0, 1 loss. So in particular, that means that if we try to use the optimization techniques, and actually just in general, it becomes hard to optimize this objective. Okay, and that's all I really want to say about this thing. There's some methods very rarely discussed about how to directly like try to minimize the 0, 1 loss. So instead of trying to minimize this thing directly, we're not going to do that. And we could like, well, we're going to find, okay, one option here is like, okay, maybe let's not use the 0, 1 loss, but let's use something that's close to the 0, 1 loss, but is continuous in some way, maybe. And is like really close, so it doesn't have these disjoint. And we're going to see that's actually what we're going to end up kind of doing, but it's kind of hard to decide what that function should be in some way. So we're going to go with a different approach, which is the second approach we had before with regression, which is instead of minimizing this estimated loss, okay, and then outputting that predictor, we're going to go through this F-Bayes approach. Okay, so we had this other method, which is like, what is F-Bayes when the loss is the 0, 1 loss? Let's like, before it was this expected value of y given x, right? And then we said, let's estimate that expected value, because like if you write it out, then there's this p of y given x. Let's just estimate p of y given x, evaluate the integral, and then we have an estimate of F-Bayes. Okay. So the story is going to be kind of similar. So we start with F-Bayes, and let's say we try to estimate F-Bayes. Well, we have this like expression for what F-Bayes is. It's the best possible predictor out of all the possible functions, right, that minimizes the true expected loss. But now, unlike the regression setting, right, the loss is different. And it turns out that if you expand, okay, like this is the definition, right, it's this expected value. If you expand this expected value, you plug in the 0, 1 loss, you evaluate, try to find this argument. It takes like some steps that maybe is a bit too complicated for this course to cover. Anyways, the point of the story is if you do this process, you end up with a nice expression for what it becomes, like what F-Bayes becomes. And in particular, F-Bayes, for some feature input x, right, it's going to be equal not to the expected value of y given x anymore. It's actually going to be equal to the argmax label. So the argmax y in the set of labels calligraphic y of this PMF p of y given x. Okay, PMF because y is discrete here. And yeah, so okay, this should make some sense. So remember in the discrete, so let's interpret it. In the discrete setting, discrete random variable setting, which is what y here is, right? You can think of these PMFs as actually exactly representing probabilities, which is beautiful. So you can really say that this is like the probability of y given some x. And this is just saying, for some feature x, which label should I output? Well, I should output the label that has the highest probability of occurring given that feature x. So like, yeah, so you get some chemical information. Each one of the labels has some probability of occurring, some like true probability. This is what this represents. And so maybe like in this case, there's 3 labels. Maybe this one has like a 0.5 chance. This is like 0.2, and this is 0.3, let's say. Well, what do? You just pick the one that has the highest probability of occurring. Okay, so that's what F base turns out to be. That turns out to be the best possible predictor you could use. Okay, so if you really knew this underlying PMF, then that's what you should output. So yeah, you can imagine what we're going to do next. We're going to use MLE or MAP, but we're just going to do MLE in this class, like in this lecture, to estimate this guy here. And then when we estimate it, we're going to see what we get. Okay. Well, we're going to get it, and then we just take the argmax, and that's our learner. Like our learner outputs the predictor that first estimates this and then calculates the argmax. Okay, so that's going to be the thing. And we're going to spend most of the class doing that, and then we're going to talk about some like interpretations of how that looks like for solving this kind of problem actually, because there's a nice mapping, and then that's going to be the class. Okay, so we just go directly into solving this problem using MLE now. And okay, so here is where the distinction comes between this class and next class. So far I was just talking about classification in general, and I gave an example where there was 3 classes. You could have as many as you want in general, as long as there's unordered objects. So like classic examples are like these labeling pictures. So you have cats, dogs, elephants, whatever. There's another like thing is like maybe you want to know what is the actual next word in a sentence, which is getting very close to what like language model and stuff are doing. You have like the feature is all the stuff in the past of the sentence, and then your goal is to predict the next word in the sentence. And there's a lot of words, right? So that means like the number of classes would be all the possible words you could predict, and so on. Okay. So the distinction here is that people like to break up classification into 2 cases. One of them being binary classification, which is your labels are either like true or not true, or 0 or 1. It's like you have that or you don't, or whatever. So there's only 2 labels basically. It's a set of 2 objects. And this turns out to be a nice, easy like case to work out first and see what happens. And then we move on to the multi-class classification, which is just like a generalization of this setting, where you can have as many labels as you want. Okay? So for this class, we're working with this everywhere. Okay, so Y from now on is just 2 classes, and we're always going to use the number 0 to represent like class, whatever your first class, and then 1 to represent the second. And the numbers just make math work out easier, but always these could be like words or whatever, like the name of a wine and so on. So you just map that word to the number 0 and 1. Okay. So now let's work things out. So like, yeah, you set up the MLE thing. What is the MLE situation? So MLE, we want to estimate this guy, right? This is the conditional PMF of Y given X. We've seen this before. What is a setting? It's like a supervised learning setting, same thing as before. You have this data set, okay, and each one of these feature label pairs, their IID, they have some true distribution, some true like PMF, PDF thing, okay. And what did we do before? We made an assumption about the conditional distribution of Y given X. And we said it was like this normal distribution, which had a mean that was like this linear function and so on. Well, now it doesn't make much sense to make an assumption that it's a normal distribution, right? Because a normal distribution, the value of Y can take, or like the random variable can take, is from -∞ to +∞, right? So we need some other distribution. A distribution that takes, that the random variables take values 0 or 1, just like 2 numbers, okay? And here it's like not really even an assumption, because like the only distribution you can have on these 2 things is really a Bernoulli, okay? So that's going to be the assumption. And that should make, but there's one part of it that is, you'll see why it's kind of an assumption. Okay, so we're going to assume that the labels, each one of these yi's, conditioned on some feature xi being equal to little xi, is not following a normal, but instead is following a Bernoulli distribution. And the thing we don't know is the true parameter of the Bernoulli. This tells you the probability of getting 1. And we're going to call this true parameter alpha star. And it's going to depend on x, right? So it's going to be like a function of x. So here I'm making it explicit that there's this parameter, alpha star we don't know, and it's going to depend on your feature xi. So for different xi's, that parameter might be different, right? Okay. So we need some function. So we're going to want to learn this parameter, and we're going to need to describe it by some function. And what we've been doing everywhere so far is like the only functions we really know are these linear functions that we've seen, right? Or it's the polynomial function which just looks like a linear function in those polynomial features. And so like in the previous case with regression, we said, oh, in the normal distribution, the mean parameter mu is a linear function. And here what we could like try to do is say, oh, maybe this thing is just a linear function as well of x, and like use that model, which is like x transpose w, right? But that also becomes a little bit funky because then like x transpose w can take values between negative infinity and positive infinity, okay? And so we'll talk a little bit about what happens if you try to do that and why it's not like a great idea, but you could technically do that, and then like you can just clip the values if they're much larger, if they're as soon as they hit 1 or -1. But anyways, a more natural choice, which is what people do, okay, is to choose a function that actually takes values between 0 and 1, right? Because that's what this parameter can be. Like, why would you predict something larger than 1 or less? Okay, so let's draw that function, then let's define it, and then we'll write it out. So this is what the function looks like. Okay, so here you have 1. This is obviously 0 at the bottom. And if you have 0 here, and we're going to have some variable z. Okay, so there's this function called a sigmoid function or a logistic function, and it looks as follows. So it's 0, 0, 0, then it passes through here, and then it never passes 1. Okay, so it's between 0 and 1. And here it's exactly 0.5. Okay, so this is some function. What is that function? Well, that function is this thing called a sigmoid function. We're going to usually, like the symbol to use for this is the sigma. And it's a function of, let's say, some value z. We'll see what z is in a second. And it just has this form. Okay, so for the first time, we see something that's not a linear function. It is this like exponential looking function thing. Okay. And yeah, you can kind of look at the extreme cases, which is if z is really, really, really large, then you get e to the negative something really, really large, which is very close to 0. And so you get 1 over 1. And so that's why here you're approaching 1. And then the other case is you get 1 over infinity, basically, if z is really negative on this side. And so that's why you get 0 there. Okay, so these are the two extremes. At 0, if you plug in 0, you get 1 over 2, because you get 1 plus 1. And that's where the 0.5 comes from. Okay, the important thing is that this is a function that if I pass in something into its input, that takes values now between negative infinity and positive infinity. It squishes it between 0 and 1, right? This is the 0 line. This is the 1 line. That is the important observation. There's like other functions that can kind of do this. And yeah, at this point, it's like there's some intuition. You could have tried other ones and stuff. And when we start working things out, you'll see that it has another nice property of like, it makes things convex later on, okay? And we needed convexity to minimize things and so on. Okay, so this is our function, and it has this name called a sigmoid. Or another one that people call it is sometimes the logistic function. And this is also an important name because we'll hear this term called logistic regression in a second here. Okay, so yeah, so this is going to be the function we're going to use, but like, okay, so what does that mean? That means that this Bernoulli thing, this alpha is going to be replaced by this function, sigma, right? But we need some function of some parameters w and stuff. So what turns out to be the natural thing to do here is you pass in the features xi transpose, and then you have this linear function with w, and then you pass it in through the sigmoid. Okay, so how do you interpret this, right? This is a parameter that should depend on your features. The way it depends on the features, oh, and I should give this a star here, is in this way, which is first the features get linearly like transformed or whatever. They get multiplied by this true parameter w star, which can give you any number between negative and positive infinity. This is the usual linear function we've seen. And then that number gets squished between 0 and 1, which is what the sigmoid does. And that actually gives you something that's like in the range of this parameter value. Okay, so this is really the big novelty of what's happened in classification, like this stuff versus the MLE before with the normal distribution. What we do next is now we're going to just solve the MLE problem. Okay. Great, no questions. Okay. So to solve the MLE problem, like we're going to try to find this like parameter alpha, or basically we're going to find this W star, like an estimate to it. And how do we do that? Well, we find that, first of all, because we've assumed that this conditional random variable is this distribution, the PMF has a special form. It's the Bernoulli's form of a PMF. And what that means is that the PMF of y conditioned on x has the form of Bernoulli. And there's this compressed way of writing it that I think maybe you saw in the course notes and we briefly talked about, which is okay, a Bernoulli, when y is equal to 1, right? What's the probability of that happening? Well, it's this parameter exactly. So for Bernoulli, this value tells you the probability of getting 1, right? So when y equals 1 here, you would like for this to equal to this parameter. And when y is equal to 0, this should equal to 1 minus that parameter. It turns out you can write this in this nice way without having these if statements and so on, as follows, which is you take the sigmoid like this, and then you raise it to the exponent of y. So when y is 1, you just get this thing to the power of 1, and that should be fine. And then when y is 0, you actually want 1 minus this sigmoid function, right, the parameter. And here you raise it to the power of 1 minus y. So when y is 1, this is 1, this is 0. So this thing is just a number 1, right? Anything to the power of 0 is just 1. So you get this when y is 1, which is why that makes sense. This is the probability of getting y equal to 1. And the probability of getting y equal to 0 is the following. And if y equals 0, then this thing is raised to the power of 0, and this thing is raised to the power of 1. Okay. Just like a compressed way to write this two cases of the Bernoulli instead of writing the if and otherwise cases. And then you can actually plug this in and take derivatives and optimize and so on. So that's really what we're going to do all next. Okay. And so I wrote out the very beginning of this MLE stuff because it's all the exact same that we have seen all before. So you want to find WMLE, which is your estimate of this W star guy here. Okay, how do you do this? You want to find the argmax parameter that maximizes this likelihood function. But then because the data is IID, what you can do is you can find that this thing is actually written as the product of all of these PDF, PMF terms, these guys. Then what you do is you don't know how to maximize this product of things. So what you do is you take the logarithm, and then since we're always minimizing an optimization, you take the negative of the logarithm and say you're doing minimization. That's this step. And then the important thing is the product turns into a sum because we took the logarithm. Okay. Then you notice, oh, this thing can be expanded using the product rule for probabilities. So this joint PMF, PDF, whatever, can be written as the product of this conditional times this marginal. And then what I've done is I've, in this step, also expanded that one more step because of the logarithm is applied on a product of two things, so then it becomes the sum of the two terms. Anyways, this is all just repeating what we've seen many times before. And then finally, we did not talk about this marginal. There's no parameter describing it. It has nothing to do with the W term. So this does not change the solution of the optimization problem. It's just shifting it by a constant. So this goes away. Okay. And we get to this thing, which is nothing new. This is where we've been many times before. Okay, and so the thing that's changed now is that this thing is a different function, right? We assumed that the distribution was Bernoulli. So what we're going to plug in next for this is not the normal distributions PDF. We're going to plug in the Bernoulli's PMF for this. So that is where we start from now. Okay. And remember, all that is to just find what is this parameter, and once we have that parameter, we have an estimate of the true parameter, and then when we have that, we're going to be able to plug that all back into here and get our actual predictor of classes. Okay, so that's don't lose the big picture, I guess. Okay, so remove this, and let's just copy and paste in the PMF that we wrote above. So yeah, this equation. Oh, and one more thing, this should be star, right? So the true PMF uses W star. Okay. So we have this, This is the PMF, and of course this is for each data point xi here and yi. And yeah, just to answer maybe a quick question is like, someone's asking, is this calligraphic x, are the features still in R of d plus 1? And the answer is yes, they're still in R of d plus 1. So, and the W is still going to have this bias term, so it's also going to be in R of d plus 1 and everything. So this, really this linear thing should be thought of as exactly the same as before. Okay. And we'll write out what the function class is a little bit later with it a bit more formally. Okay. So yeah, so we got to here. All I've done is literally plugged in what the definition of this thing is, right? So nothing special there. But now the logarithm kind of comes to save the day with products of things. And what do we have here? We have a product of two terms. And so the logarithm becomes the sum of those two terms. So let's do that. Yeah. Let's make this a bit smaller. So now we have the sum of these guys. So there's the log plus the log again. Okay. Now there's another logarithm property that is really useful that I maybe haven't mentioned before, but it turns out that the log of x to the power of a, which is what we are seeing in both these cases, right? There's these powers, is actually equal to, and I guess you saw this on the midterm, is equal to a times the log of x. So yeah, you can see that applying log on things for optimization turns out to be a very useful thing to do. Okay, so we use that property and expand this guy out, or simplify. Make this a little bit smaller. Okay, so no more exponent, right? And now that exponent comes out to the front. So it becomes yi in front. Similarly with this guy, the exponent goes away. And it comes out to the front. Okay. So that's where we got to. And it turns out that this is like as much as we're going to actually end up simplifying this thing. And at this point, we're just going to just solve this minimization problem. Okay, so yeah, we want to minimize the following thing. So let's do that. First, there's a, okay, so let's call this thing something. Let's call this a function. So we're going to call this thing a function of the parameters w, right? We're going to call this thing g of w. So we're going to try to find the minimum of this. How are we going to do this? We're going to use like the derivatives and try to set it to 0 maybe and stuff like this. But one important property to be able to do this is that things need to be convex. And it turns out that this function is indeed convex. And that is one other good reason to pick this sigmoid function. So if you pick the sigmoid and stuff here, it turns out that when you write this thing out, you end up with an objective that is indeed convex. And so that means we can really find the optimal, like the minimizer. Okay. So now we just work out some derivatives. And this is, okay, this takes a few steps, and we have to do some substitutions and a few chain rules, but we'll get there. So here's some new definitions. So I'm going to define this term ui as this linear function xi transpose w. I'm then also going to define this thing called vi, which is then the sigmoid applied to ui. And then I see, oh, here's vi, here's vi. And so I give these two things one more name, which I'm going to call this like hi is a function of vi here. And I'm going to call this whole thing another function called ri, which is a function of vi as well. Okay, now I just do a bunch of chain rules to get this derivative. And what that looks like is, the thing I'm interested in is the partial derivative of this function g with respect to wj. Okay, so j, I'm going to do it, so w is a vector, and as you recall, when we do these partial derivatives, I'm going to do it for each index j. So, and this becomes some function of w. So what does this thing look like? Well, first of all, you can, like, the derivative of a sum of things is equal to the sum of all the partial derivatives inside the sum, and then these are the terms inside. So we're going to do a bunch of chain rules inside. So first of all, this becomes the negative sum And then we have a bunch of partial derivatives inside. So first thing is like the h, so it's going to be actually just like the regular derivative of h with respect to vi. So there's this guy. And then I'm not going to keep writing this kind of thing because it's very annoying. So I'm just going to remove what it's a function of, like throughout basically from now on. Then the next step is you want to take the derivative of vi with respect to ui. And then you need to take the derivative of ui with respect to, and this has to be a partial derivative now, with respect to wj. Okay, so that was for this first term. And now you do a very similar thing for the second term, which is you take the derivative of ri with respect to vi. Then you take the derivative of vi with respect to ui. And then the partial derivative of ui with respect to wj. And that is your whole derivative. Okay, so all that we need to do is work out a bunch of these like partial derivatives, and we can do that just on the side here. And they're all quite straightforward. So first one is this d of the derivative of hi with respect to vi. If you look at it, it's just this function. But what does that function look like? That's just yi times the log of what is vi in there. And the derivative of the log of vi is just 1 over vi. So this guy's easy. This equals to yi is just a constant here, times the derivative of log vi. That's just 1 over vi. Okay. And like if we plug in what vi is, we end up with yi over the sigmoid of ui. Okay, so that's good. Next one is let's do this guy here. So this term is the derivative of ri with respect to vi. This one's a little bit more complicated, but I'm just going to kind of do it quickly. So this is a constant here. And then you have the log of 1 minus vi. So the derivative of that turns out to be 1 over this thing inside, right? That was the same thing as before. But then you also need to take the derivative of the inside term, which has this negative. So it would be the derivative of negative vi. So you get a negative out front. Okay. So that all to say is you get 1 minus yi times, you have this, so we had this 1 over 1 minus vi term, right? But then there was like this whole negative out front. So I just put it there. Okay. And then once again, if you plug in what vi is, you end up with 1, like this negative, and then you have a 1 minus yi up top, and 1 minus sigmoid of ui at the bottom. Okay. And then a few more derivatives. So these are the exact same. So, okay, what's a derivative of vi with respect to ui? Turns out this one actually is a little bit more complicated, and I'm going to avoid doing it in class. But it turns out that if you do this derivative, you end up with this nice expression, which is the sigmoid of ui times 1 minus the sigmoid of ui. Okay, and I leave this as an exercise, I guess. Because otherwise we'd be really going down another chain rule path, and yeah, I don't know if that's that useful. Okay, and then the last derivative, we've seen this one a lot, is just the derivative of this term with respect to wj. And so if you expand this dot product out, you end up with like xi1 times w1, or well, xi0 times w0, and then xi1 times w1, and plus so on and so on. And so what you notice is that the wj term is only multiplying xi of j. And so that's what that derivative is. Partial. Okay, so that should all hopefully be quite familiar and simple. And so you just get xij. J, not y. Okay, so we've worked out these things. Let's plug it in and see what we end up with. So this is our expression. And okay. And so what I'm going to do is plug in all of these things in here and simplify. And it's quite interesting what we end up with, actually. Another potential coincidence. Okay, so yeah, let's plug in these things. So here we have the first term is yi over this sigmoid of ui. That's just this guy. And then it's sigmoid ui times 1 minus sigmoid ui, right? And then times xij. And then that's all minus this guy, and then the same terms. Okay, why do I have the minus? It's because of this. So I'm changing the plus to a minus now. Okay. And then this is exactly the same. So I just copy it and paste it to make that very clear. Great. So we have this whole expression, but take a look. There's some very nice observations here, which is that this cancels out with this denominator cancels out with this numerator. So this becomes much more simplified. And so this guy goes away, this guy goes away, this guy goes away as well, and this guy. Okay. So we end up with this expression, and we simplify even further by expanding this out. And we're almost there. Yeah, so if we expand this out, we multiply through, we get that the first term is just yi times xij. The second term is minus yi times sigmoid of ui xij. And then this guy, okay, let me just erase everything. Is equal to minus sigmoid of ui times xij, and then plus yi sigmoid of ui xij. Okay, we're basically there. Like, the thing you notice is that, oh, the second and fourth term are the same, so these can cancel out. And so you're just left with this yi xij minus sigmoid of ui xij. Okay. So some observations. So like this xij is the same, so I could take it out of the expression. So I'm going to do that now, actually. And okay, so we got this expression, and I'm going to simplify just a slight bit more, but I'm going to write also what is this whole thing, right? This was the derivative. So what we got is the partial derivative of g with respect to wj, which is a function of w. And what does that equal? I'm just going to like expand the negative inside of the thing so that these two things swap. And then you should see that this is a very interesting expression. Okay. And I'm going to plug in what ui is, right? ui is xi transpose w minus yi and xij. Okay, you might remember what the derivative was for this like whole linear regression setting with the squared loss or with the normal distribution assumption in MLE and so on. And you might remember that it's almost the exact same thing as this. The only thing that's different was that there we had a 2 because of like the squared part came out from, and that this was not this sigmoid, but it was just this because we assumed that there was like the parameters were a linear function. But otherwise it had the same exact form, which was like the assumed model or the assumed whatever function for the parameter minus, oh, how did that happen? Minus the label all multiplied by xij. And we're not going to cover this in this class, but it turns out that this like Bernoulli assumption with this parameter and the normal one we saw before, they all belong to this like more general class of assumptions, or like the distributions called this exponential family of things. And these type of models we're assuming here are called these like generalized linear models. And they almost all have this kind of, they basically all have this expression, except they're multiplied by like a different constant out front. Okay, so this doesn't turn out to be quite a coincidence. Well, maybe it is a coincidence here, but then it turns out to be part of this like maybe larger class of theory and stuff like that. But we don't cover that in this class, but the main takeaway is, yeah, there's like, this is our derivative, and it turns out to be very, very similar to the one that we saw before for regression. Okay, so what do we do with this regression, with this derivative now? And so the natural first thing you'd want to do is get a closed form solution, right? That's what we did before. We have this, okay, so this is the derivative for j 0 to d. And what did we do before? We wrote out this like system of d+1 equations, and then we rearranged some things and got these matrices, and then I said, oh, there's a closed form solution for this by like just solving this linear algebra problem. So I'm not gonna, well, we can try doing all that, but it turns out that if you try doing all this, there really is no closed form solution. Okay, and so here we finally see our first case of having no closed form solution for a problem we actually care about. And so here we really are kind of like we're required to use something other than just the closed form solution. And here we use our new, or like the other tool we know, which is gradient descent. Okay, and so that's what we're gonna do. And just like in general, when we start assuming more complicated functions to describe our parameters or for our predictors, when like we output the predictor, like such as a sigmoid, and what we're going to see in 2 classes for now, which is this is not going to be a sigmoid function, it's going to be a neural network that does some more complicated steps on this. But like if you make the function more complex, what you're going to get is no more closed form solution, and you're going to have to use gradient descent. So yeah, gradient descent's pretty straightforward once you have the derivatives. So like how does gradient descent work, right? Well, you just update the parameters one epoch or iteration at a time as follows. So you have this update rule, nothing different than what we saw before. Like this is just copy and paste from before. And all you need is the gradient of whatever function you're trying to take steps with respect to. And that's here is this g of w. Okay. And like we basically have the gradient almost. We have the partial derivatives. What is the gradient? It's just like a vector of all these partial derivatives. And since this thing has the very similar form to before, it turns out if you just write out what the definition of the gradient is, you will find that it has like these terms. Okay, these are all constants with respect to j. So you can just like factor that out, and this thing becomes, you can write it out as a vector. And you get this nice compressed version of writing what it is. So we've seen this before, and I leave it again as a exercise for you to work this out, but you get that this thing out front, this whole sum, is just a constant in terms of j. So you can just take it out. It's always the same for all the partial derivatives, right? No dependence on j here, so this is always the same for all the partial derivatives. And the only thing that differs between all the partial derivatives is the xij term. And so you can write this whole thing as a vector by, instead of doing xij, you just do xi vector. Okay. And this whole thing, as a gradient should be, is an element of Rd plus 1. Great, so this all should make sense now. Like you have a parameter that's in Rd plus 1, and what is its update rule? It's the previous parameter minus some scalar, some constant, times another vector in R of d plus 1, which is this gradient. This is what we've seen many times. Okay, so where did this get us? What it got us is that we wanted WMLE. Right, that was our goal. But we couldn't get actually exactly WMLE. We had to get an approximation to it using this gradient descent stuff. So if we run gradient descent for longer and longer, we should get close or sometimes exactly WMLE. So we end up with that this W for some number of epochs, capital T, is an approximation to WMLE. Okay. And then okay, what does a WMLE thing buy us? Well, it buys us that this, if you plug in WMLE into the sigmoid function for some feature x, and you plug in WMLE, okay, well, then this thing is approximately equal to the true parameter, alpha star, for that x feature. Okay, so once we have WMLE, or our approximation, if we use that, then it's an approximation to the true parameter, which is the thing we're trying to estimate. And what does that true parameter tell us? It tells us this is the probability, right, that the label is the number 1. That's what the parameter for Bernoulli tells you. It says this is the probability of getting a 1. 1 minus this thing gives me the probability of getting a 0. Okay, and I'm going to call this thing the MLE function, or just, I guess, simplicity of writing things. So this is what Emily tells us. It gives us, once again, the probability of getting the label 1. Okay. What we don't have quite yet, is like a way to predict 1 or 0, right? So far we're predicting the probability of getting the label 1. And so that's going to be the next step, is like, how are we going to choose to use these probabilities to then choose if the class should be 1 or 0? And it's like a very trivial way how we're going to do this. And okay, like you could probably naively try to do this, but the way we're going to do it is we're going to plug it back into this F-Bayes business and see what happens. So we want, at the end of the day, we want what I'm going to call a binary classification learner, right? So this is kind of our goal. And what that should look like is you have this like learner takes in some data set, outputs, let's say F hat binary. Okay, what is this F hat binary going to be? Well, we're going to get it through this initial process we started off claiming we're going to try to do, which is through this F-Bayes business. Okay. How do we do that? Well, we're almost there. All we needed was an approximation to this thing, which we have now. So let's plug that in. And notice that the y is just like the set 0, 1. So I'm going to write y is an element of 0, 1. And now I plug in, what is it like? Okay, so this thing is the following. Okay, so we can use this WMLE to get this function. And this was like that nice compressed Bernoulli function, whatever. And then we need to take the argmax. Okay, and I'm going to talk a little bit more about interpreting this, well, actually quite a lot more in a very short second. So before I do that, I'm going to say that this thing now, this approximation to F-Bayes, is what we're going to call F-binary, or F-bit. So that's what our learner is going to do. Our learner is going to output this F hat, which is just the solution to taking the argmax label, so the label y, right? That gives the largest probability of seeing that y. There's some probability of seeing 1, there's some probability of seeing 0. That's based on the parameter WMLE that we learned, and we're going to pick the largest one. But this turns out to be you can interpret this in a very simple way because there's only 2 probabilities, right? And the probabilities have to add up to 1. So here's the way people usually interpret it. It allows you to be able to plot things nicely as well, which you'll see in the assignments and stuff. And that's why this binary classification stuff is also very nice to start with. So what does this mean? Okay, this function, this y can only take on 2 values. So we can just look at what is this equal for those 2 values. And we've seen this already, but p of y given 1 of this function, well, that's just equal to FMLE, right? That's what I was saying this whole time, is that FMLE is the probability of getting 1. And then obviously the opposite is also true, which is the probability of getting 0 is now going to be 1 minus this thing. So that equals to 1 minus FMLE. Okay. So that's what this it's really saying pick what's larger, FMLE or 1 minus FMLE. Okay. So I can write that in this conditional form, which maybe makes. So all this is now just interpretation of what we're outputting, and then I'm going to plot some things to even understand it further. Okay, so what is this F binary? So it outputs either 1 or 0, right? It's picking the argmax of this. So when is it 1 and when is it 0? Well, it's equal to 1 if FMLE is obviously larger than this, but FMLE plus this, these are probabilities, they have to add up to 1. So that's really if FMLE of x is greater than, and we're going to do greater than or equal to 0.5 here. Makes sense. If it's higher than 50%, there's only two options. If it's a higher than 50% chance, I'm going to output that one. That's what the argmax means. And 0, and I'm going to make it explicit, which is the other case, which is less than 50%. Okay. One more way to think about this is to recall what FMLE is. And FMLE is the sigmoid of this X transpose W thing. And if we go back to the plot of the sigmoid, you will notice when is the sigmoid greater than 0.5? Like, so this is this point. Well, that's when z is greater than 0. And what's z here? It's x transpose w. So when our linear function, x transpose w, is greater than 0, our sigmoid is like, it's over here, and it's greater than 0.5, which is exactly this, like, the rule for when we output y equal 1 or 0. So it turns out that you can also think about it as follows. And all these things are useful for plotting. So you can think of 1 or 0, not for fMLE, but instead for when this linear function is just greater than or equal to 0. And the other case is obviously when it's less than. Okay. Great. Yeah. So why do all these interpretation stuff? It's because people, like, it's really nice to be able to plot what does this, like, this decision rule and stuff look like in, well, you can plot it, and the way you plot it is you actually plot this thing here. And you plot this like what does that mean? Well, there's one more kind of step, which is that if you look at this equation, x transpose w MLE, right? What does this thing look like? It's just like w naught plus x1 w1 plus all the way up to xd wd equal to 0. And it turns out that this thing is actually like, well, what's called so this is a d minus 1 dimensional hyperplane. And like, what is this hyperplane thing business? Well, like, if d equals 2, then a d minus 1, so a one-dimensional hyperplane is just a line. If d equals 3, then a d, like 3 minus 1, so two-dimensional hyperplane is just a plane. And then when you go past that, people call these things hyperplanes. Okay. And so the easy way to, okay, so now we're going to plot things. And to see with this hyperplane terminology and how you get a line and stuff, let's do it for the case of d equal 2. And this is like the classic thing you'll see in a lot of these classification things. And this is called plotting the decision boundary that you output. Okay. So let's interpret what's going on here. So first of all, d is 2, right? That's the dimension. Second thing is we have data, and I'm plotting the data set. Okay? And we have two features. I'm plotting the two features, x2 and x1. I'm not plotting x0, that's just a constant 1 all the time. Now I need to plot the value that, like, what is the label, right? So like for these features, every single data point has a corresponding label. So instead of plotting it in 3D, I'm using a different object for that data point to resemble 1 or 0. So x means y equals 0. Circle means y equals 1. So you can think of this in a third dimension. You would just have like these like binary 1 or 0 height. Okay, so here we see that, oh, when this feature is large and when this feature is large, it seems that I'm getting the label y equals 0. And when it's smaller, I'm getting this label of y equals 1. And then there's like some overlap and so on here. Okay. So what is this thing that I output? Like, what is f bin? What is it going to do? Like, what's a good classifier going to do here? Well, what you would expect is something like, well, yeah, maybe it's something like, if it wants to really fit it, it would fit something like this. But here we're going to find out we're actually limited to lines. So maybe it'll fit something like this. And so how do we see that we have lines and that this is what it becomes? Well, we know that our decision boundary, or like our decision is to be 1 when this equation is greater than 0, and it's going to be 0 when this is less than 0. So that's going to be like what we predict. So let's plot this exact case when it's like the point at which the decision changes. In particular, let's plot like that. That's why I was saying let's plot this equation equal to 0. That is exactly the point at which these two cases switch from 1 to 0. So that's our output switches. Okay. And so how am I going to plot that? Well, let's write it out, this equation for the two-dimensional case. And we see that we just get an equation of a line, is what I'm trying to get at. Okay, so in 2 dimensions, you have w0 plus x1, w1 plus x2, w2 equal to 0. And you can think of this x2 as like, the y value of your plot, not the actual y label, but I'm just saying like from, this y equals mx plus b equation business that you've seen before. So let's isolate for x2, and then you can see you get a linear equation. Okay, so what you will get is x2 equals 2 minus x1, w1, minus w0, right? All I've done is move the terms to the right, and then I divide by w2 everywhere. So then I would divide by w2 and w2. And so this is just your classic equation of a line, which is like your y-axis or your vertical axis is equal to a function of the x-axis scaled by some value. This is like your m times x term. And then here's your intercept. Okay. So that means I can plot this thing as a line. And what you will find is that, what you'll find at the end of the day is that this like binary predictor will just be a line. And that line, if it's good, will look something like the following kind of thing. Okay, so it'll be this line. So what does this line tell me? Well, what you should see is that here, like so in this region here, that X transpose W MLE, okay, is less than 0. Why? Well, because that should be the case where we predict 0. And if we predict 0, that should be mostly correct here. So that's what you can like interpret. So that's what this thing should look like. And that would also map to F MLE. Or, yeah, F MLE is going to be obviously less than 0.5, or what we really care about is this F binary. Like this is our actual predictor. And so our actual predictor would output 0 in this case, right? Once again, when this thing is less than 0, our predictor outputs 0. Okay. So everything here, like all this, our predictor for any value of feature there, like for any value of x1 and x2 that's in this region, our binary predictor will output 0. That's what this plot is showing. And then on the other side, of course, then our binary predictor will output 1. Okay, so this is a really useful way to plot these things. And then you can see that, yeah, these decision boundaries, like if you get, so as you like do more and more iterations of gradient descent, you're going to get like something closer and closer to FMLE. And what you'll see in like the assignment is that if you like change the slider of how many epochs or whatever, like then you'll get something that's a line that's like closer. Like you might start with something here, which is terrible, and then you're going to get closer and closer to like splitting these apart until you get like the best possible split kind of. Okay. And the question was something like, why is J up to D, but our domain is D plus 1? Well, it's because J includes 0. So this is 0 to D. That's the D plus 1 indices. Okay. In the notes, I guess I mentioned this later, but I'm going to mention now. Yeah, which is like, you can, yeah. So far, you look, this decision boundary is linear. Like, why is it linear? Why is it a line? Because we assume that the thing inside the sigmoid is a linear function. How do you change this to not be a line, like we've seen before? Well, you assume that here instead of x, you use polynomial features. And then you will get, instead of a line here, you'll get a polynomial decision boundary. So you can really get something much more fine-grained than like this thing if you choose it. So, and I'm not going to work through all that, but like once again, everything just applies. So like polynomial features apply like before in every, like everything just works out the exact same way. And also like map implying like kind of this regularization stuff also works out the exact same way. Okay, so yeah. So this is what I mean by like the stuff we've learned before really maps beautifully here. Like all we've done is just change the MLE problem slightly. We get to something that like, okay, it's a different like predictor, but yeah, you can use polynomial features to improve this decision boundary to be like this more complicated looking thing. You can use regularization in the same way. You can like start with a really large polynomial class and then change your regularization parameter to make this simpler or more complex. So like if the regularization parameter was really, really large, then you would get something that looks like this line. But if it was really, really small, then you really get some very complicated looking predictor if you started with a complicated function class. Yeah, that's all I have to say about that stuff. So, okay, so now there's more things to interpret and what this stuff is. Okay, so we have this like binary predictor thing. Okay, so any questions about this before I go into two more things, which is like thinking of this as like actually solving, like minimizing an estimated loss, which we haven't quite done yet, and then talking about why using the squared loss and stuff is not like a good idea very briefly. Okay, cool. Okay, so this part I think is kind of cool and fun, and the name. So far I haven't really given you much terminology or like the name for this, but like people actually call this whole thing that we were doing this term called logistic regression. And this might be a little bit misleading or like weird because like people are like, you know, when you have these like continuous valued labels and stuff, you use regression, you do like linear or polynomial regression or whatever. And then when you move on to classification, people are like, let's solve it with logistic regression. It's like, why are we doing regression again? Like, how are we doing regression to solve classification? And people will just like plainly say, okay, I used a logistic regression like learner or whatever or model to solve classification. But like, where does that map? And so here's the mapping, or like, here's the relationship of these things. So first of all, you should already see where the logistic part comes from because we're using logistic functions, right, as our predictors. Before, when we were using linear functions, we called it linear regression. Here we have logistic. Okay, but why are we solving a regression problem? Well, because you can think of what we're doing as actually solving a regression problem in this sense. So look at what is the process for outputting F binary? Well, you can think of the process outputting F binary as like this binary classifier as first trying to learn or like get a function to predict this thing, this probability, right? And in particular, the probability of y equals 1. So that was this thing here. And what was that? That was like this FMLE. So FMLE, you can think of as being a predictor that predicts this parameter, this probability here. And this probability is a value, a continuous number between 0 to 1. Okay, so you can think of first solving a regression problem, which has labels as this parameter, which tells you the probability of having y equals 1. You just need that one parameter, that one probability, because the other probability is just 1 minus it. Okay? So you just have that one number that you need to predict. That's your regression problem. The y values are between 0 and 1. And then once you solve that regression problem, you get this thing which predicts probabilities, right? This FMLE predicts probabilities. You then use the solution from that regression problem to then output your classification, whatever result in this way, where you just take the argmax. Okay. So really what's happening is you can think of this as solving a regression problem and then use your solution in this argmax way to output the corresponding class. Okay. And it turns out you can also like, people can then, what they do is they're like, okay, maybe instead of just outputting F Bayes with this like exact decision boundary of 0.5, I will change the decision boundary to be smaller or bigger based on my case. Maybe like I really don't want to like mess up my prediction to be like so in like some critical scenarios or something, you really don't want like false positive or something. You don't want to predict that someone's, let's say, not sick. That means like 0 or something. If they really are. So maybe you want the boundary to be much, much smaller or something. So like you predict they're sick, even if the probability is like 10%. So you might change this to like 10% and so. Okay, that's just like a slight note. Okay, back to the interpretation of regression. So let's set up this regression problem now. So now our labels are no longer 0 and 1. Okay, we're going to have this set of labels or targets as now this continuous interval from 0 to 1. And what is it representing? It's no longer representing the class. It's now representing the probability that the the underlying thing we actually care about, the class being 1, is equal to the probability of that class being equal to 1. And so here this is a little bit sloppy with notation, but I think it's better to just keep the y's the way I'm doing here. So like we want to predict the following, which is just this probability. The probability that the true class, like the thing we actually care about, is equal to 1. Okay. And so from now on, like, forget about this y. You can just think of this like this is just a number, right? There's some true probability for every single x of your like class being 1. And now you're trying to solve that problem, which is to predict that probability, just the probability of the class being 1. Okay, so now that's what these y's are going to represent. So y from now on is always representing probabilities, like for this section. Okay, so now we can like, okay, so now what's the loss that we're going to use? Okay. And so the loss we're going to use is no longer this like squared loss, but it's going to be this thing that's a cross entropy loss. This is what it's called. It has some like, there's a reason this word cross entropy comes up. It's from information theory. It's a bit of a longer story, so we're not going to get into it. And like, okay, maybe let's just say this is the loss we use. Let's work out some things, and then I'll come back to where it comes from in a bit later. Okay, so I'm giving you this loss, just like it's coming out of nowhere for now. But yeah, you have this loss function. And now what is your function class? Well, I'm calling it logistic regression, so my functions are going to be these logistic functions. So this looks exactly the same as we've seen before, except the only difference is that instead of this being a linear function, it's now sigmoid applied on the linear functions. So all the functions in this class have this form, sigmoid applied to linear function. Okay. Beautiful thing again is that you can think of every function in your function class, like every predictor in there, as having a one-to-one relationship between a parameter W. And so then you can optimize over your parameters W. Okay, and then the process turns out to be really straightforward in the sense that we've already worked out all of the steps. All I have to do is just write out what is this learner, and you'll see in like 2 lines that we've already solved the problem. Okay, so here's our learner. This guy is going to be like f binary, but like it's not going to be f binary. This is like our f hat that's trying to predict probabilities. So we're not solving the classification problem yet. We're just solving the problem of predicting probabilities. And that is just this single probability for now. Okay. So that's what this learner is going to output, this f hat. How is it going to do it? Well, it's in the same usual way, which is that this f hat is going to be the argmin f in this like logistic function class of the estimated loss of the predictors, right? And this thing is just like the sample mean of our loss function L. So let's write that out. And that turns out to be a very interesting looking equation. In the sense that I'm going to take this equation, and all that I'm doing is taking the sample mean. So I'm using, I get 1 over n times I equal 110. That's the estimated loss part. And here I have I for all these guys. Okay. We need one more step to make this look like exactly the same problem we were solving before, which is, okay, notice how, okay, in optimization, if you scale your function by a constant, such as 1 over n, it turns out that doesn't change the result. If you take some function and scale it by some number, it just, everything gets bigger, but the minimizer still stays the same. Okay, so it turns out this term doesn't change anything. We've seen this before, right? So, and we've seen this in the relationship between, remember, our ERM solution and the corresponding MLE solution from before, which is that there's a difference in the scaling of 1 over n. Okay, so you remove that. That doesn't change the optimization problem. One more thing we're going to remove is this minus sign. We're going to move it out front. And what we will find is that this problem, this argument thing, is exactly the thing we were solving earlier on in MLE. It's exactly, where is it? It's exactly this equation. Okay, so if you choose this loss, well, like you can see how I've handpicked it to be exactly this type of thing, then you get to the same thing, and you end up with that the MLE solution is actually the solution to this regression problem here. Okay, so in particular, this f hat becomes FMLE. So this and that should make sense. Like the FMLE thing was predicting, right? It was getting an estimate of what is this probability? What is that parameter, right? This thing is the same thing as that alpha star of x term before. Just a number. Okay, so this is the interpretation that like logistic regression, we're doing regression, but now on predicting probabilities, okay? Yeah, and so I think it's like, so it's usually, and I think it's much more natural to present things in the way that I presented, which is you go through MLE, and then you say, oh, you can also just think of this as, forget about all the MLE stuff, you could just think about solving like classification as, first you solve this problem of finding the probability of the class being equal to 1, using like regression in this way and stuff. And then I would just pull out this loss function out of a hat and just be like, this is the loss we're going to use, and you should just believe me, we should use it. And it's kind of weird why we would use it, but and then you can just, everything looks the same. And so it's usually a little bit weird to just like pull this out of a hat and start there. So We go the other way, and then we find that there's some reason that this loss might make sense, because it's the one that you get from the MLE thing. And you can also look at this loss and see that like the loss really does get close to like the 0, 1 loss, in the sense that like when y is 1, right? Well, yeah, let's do the two cases. So like when y is 1, right? If your predictor outputs something close to 1, is the loss close to 0, right? That's what the 0, 1 loss should be. So like if my prediction is close to 1 and y is 1, then I should get something close to 0. And I will, because when y is 1, this term goes away, so this is 0. And then when the predictor is 1, then I get log of 1, which is also 0. Okay. So there's this basically this balance between these two terms. And then you have the other case, or sorry, then like, yeah, if you are off, like if your prediction is wrong, meaning you predict 0, but the true label is 1, what you will find is, okay, this thing is still 0. However, this term, right, y is 1, but now you get something that's like log of 0, which is a very, very, very big negative number, right? Like, yeah. So I don't even think log of 0 works. But yeah, so like your prediction can't be exactly 0, but yeah. So usually you'll clip this and you'll see this in your assignment. But the point is, yeah, you get a loss that's very, very large. Wait, it should be 1. Okay, anyways, I'll think about that after. But yeah, it should be very close to the 0, 1 loss is the point. Okay, so that's what I have to say about logistic regression. And then like, of course, to do binary classification, what you do with this logistic regression learner stuff is then you would use this in exactly the way we've used above, which is you plug it into here, or like, I mean, really you have this, you say that F binary is just making use of FMLE in this way, or F hat that you just got, the logistic regression function. And then there you could like, yeah, you could say you can change these 0.5 if you really want to change, and this is called your like decision rule or decision boundary cutoff and stuff, and so on. Okay, and then the last thing I wanted to mention was, why use this like logistic function? Especially like here, we might have just naively thought, okay, let's use the loss function as like the squared loss maybe, and then just let's use linear functions. And like you can actually kind of do that. You can like still go ahead and try, but you'll find that it's not as good in certain cases for the reason I'm going to highlight in a second. And in particular, what I mean by that is like, yeah, you use the squared loss function here. You use linear functions as your function class. And then, yeah, you try to estimate this thing. And even though this thing should be between 0 and 1, you now can output values between negative and positive infinity because you're using these linear functions. But once you get this like predictor at the end, you need to get a classification like predictor. So how are you going to do that? Well, you do it in the same kind of way, which is you would then just have like this kind of decision boundary. But now this thing, well, yeah, so you would do the same thing, where this thing can be very, very large or very, very small, and you just do that. So you don't have this like FMLE step or anything. You literally just output this and then predict based on that. But what happens is like the following kind of problem. Okay, so this is the last part, which is why not just learn this guy, right? This is the probability of y being equal to 1 using linear regression. So that's like with the squared loss and just linear functions. And the reason is the following. So you can think of what the logistic regression setting is doing is like this. So like this is the case where d equals 1 now for this plot. So you just have one feature x1. And now the y-axis really is the labels. So you don't have the third dimension. And so, yeah, the labels are either 0 or 1. So you can see that when the feature is small, you get something close to the labels being close to 0. Like, well, they're basically 0 most of the time. And then as the feature starts getting larger, the label starts becoming 1. And then there's some point in the middle here where there's like, it's either one or the other or something. Okay. So what's this like logistic function in the decision boundary doing? Well, it's saying, okay, you might learn something like this. So this might be the solution for the MLE solution. And at this point, at 0.5, so everywhere after this, you would predict, like everywhere after this, for any x after this point, you would then predict your label as 1. So that would mean you predict the label as 1. Once again, that's because this sigmoid thing after this point is larger than 0.5, right? The other way to think about this is that the linear function that's being input to here, right, it evaluates the 0 at this exact point, at the 0.5, and then afterwards, so here, it now becomes positive, and left, it's negative. Okay, so that's a decision rule. So like here you would say 1, and here you would say, like, yeah, less than that you would say 0. That's how the binary classifier would work. How would the linear classifier work? And here I'm going to slightly overload like the terms here, but you would learn a linear function. So instead of using the sigmoid to do your predictions and say like, oh, when the sigmoid is greater than 0.5 or when the sigmoid is less than 0.5, you would learn a linear function like something like this maybe. And then you would say, oh, when my linear function is greater than 0.5, because my linear functions are now representing probabilities in linear regression, right? So linear regression, I'm using linear functions to represent probabilities. In logistic regression, I'm using logistic functions to represent probabilities. So then this linear function, which is for a different w, so this green w is different than the other one, I would then use something like the following decision boundary. So okay, so here everything looks fine and dandy and everything. It will be pretty similar in this kind of data set. The problem happens when you have the following, which is like, if you have a data point all the way out here, right? Well, then this like linear regression learner has a problem, or like it has some difficulty with this, because this data point, if it used the same predictor that it output there, this data point would have an enormous loss. Like, right, what is that loss? The loss would be like, the linear regression predictor would predict a probability of like up here of like 4 or 5 or whatever. The true label is 1, and it would have like this squared loss difference here, so it'd be enormous. So the linear regression learner would really not want to predict like points that are far out, like where the feature is like a large number. We would not want to predict those poorly. And so what you'll find is that this linear regression learner then really gets like skewed to make sure that this guy is not causing for a huge error because we're using the squared loss. And it would look something like this. And now you would have like this decision boundary over here, which is when this guy is equal to 0.5. And yeah, and so now you'd be predicting 1 here, but you would be predicting 0 all the way here, which is probably but turned out to be much worse because there's a lot of points that should actually be 1 there. Okay, so this is the problem with doing linear regression stuff, is if you have like data points that have that the feature can vary a lot. So like here, maybe it's like the feature is like some small number, and then for a very large number, and it's the same class, you have this like huge kind of shift in the predictor. Okay, but otherwise, yeah, if your feature like data is not too spread apart like this, then it's actually sort of okay to use the linear regression. Yeah, so that's all there is for binary classification. And what's going to happen next class is we're going to now care about the case where you don't just have 2 labels, like you don't have just 2 classes. You can have multiple classes. And like then you're going to be like, okay, wait a second. Like we only learned one parameter. Like we used all these like parameters these weights and stuff to learn one probability, which is the probability of y equal 1. And then that was enough because we knew the probability of y equals 0 is just 1 minus that. How do we do that now if we have 3 classes? Like if I learn the probability of y equals 1, all I know is that the probability of y not equaling 1 is 1 minus that. And now what we're going to do is we're going to find that we're going to need a new set, like a new predictor, kind of, for every single class. Okay, or we're going to need for number of classes minus 1 actually. And that's what's going to happen. And then we're getting into like slightly more. Okay, and then maybe one last point is like and we'll talk about this in the language model stuff. But like what these language models are doing is they're really solving a very similar problem to this, which is their features are all the like your sentence or the context or like whatever you input, and they're just trying to predict your next word, right? Which is very similar to what this is like. It's just trying to predict what is the next label, like what is that label given X? Is it 1 or 0? In their case, they have multiple words to predict, and then how they have to choose which word, and so they really like which word to output, and like there's different choices, but like one natural one is just to pick this argmax one, with the one that has the highest probability of occurring at the end of it, and we'll get more into it, but like you can hopefully see that this is getting very, very, if you can just predict the most probable next word, then you can just pick it and keep generating new words over and over and over again. Okay, so I ended there, and we will get into this multi-class classification next lecture. Okay, thank you.